The goal of this lecture is to go over some of the materials on higher order filters, particularly starting with the bandpass filter, and then to look at sort of just a summary of how everything pulls together in designing and implementing these filters. So because our circuits in the active filters are constructed of op amps, and because of the characteristic that the op amp has an infinite input impedance, basically the transfer function of a circuit that is a cascaded low-pass filter, high-pass filter, and inverting amplifier circuit is such that the output transfer function is the product of the transfer function of each of these stages. So if we look down here in this equation, V out over Vn will basically be the product of the low-pass filter and the high-pass filter and the feedback over input resistor of the final stage. So the low-pass filter stage is used to set the upper cutoff on the bandpass filter. The high-pass filter stage is used to set the lower cutoff on the bandpass filter. And then the inverting amplifier stage is used to set the gain. So the advantage of using the cascaded active filter for a bandpass filter is that you can independently adjust the upper cutoff, the lower cutoff, and the gain, as opposed to the passive filter where those three quantities are interrelated. If we now multiply these all together, we come up with this equation here, and then we can multiply this denominator, giving us this equation here, equation 15.10. So this is what happens if we construct a cascaded op-amp bandpass filter. This is what our transfer function looks like when it's multiplied out into a polynomial, where k is the gain. Now, remember from chapter 14, and it's important to point this out because there are some key differences between active and passive filters. So in chapter 14, when we discussed the passive bandpass filter, which is basically constructed from an RLC circuit, we came up with this equation where beta is the bandwidth and omega naught is the center frequency. And you'll notice that equation 15.10 does not have the same form as the equation that we derived in chapter 14. The only way that this can happen is if this is what we refer to as a very wide bandwidth filter. In other words, omega C2 is much, much greater than omega C1. So in this case, omega C1 plus omega C2, this term in the denominator of equation 15.10, that can be approximated as omega C2, in which case omega C2 can be substituted for that, and then we get an equation that looks like this, where the center frequency would be the square root of omega C1, omega C2, and the bandwidth would be omega C2. So that's just an approximation, and so what we'll find out is when we actually go to do actual filter design, our outcome is going to be slightly different than our design, and that's for a couple of reasons. One is if we're designing around this equation for our transfer function, remember that this is an approximation. The other is that, remember, Bode plots are additive. If these two frequencies get too close together, then the slope approaching the asymptote of one of the filters interferes with the slope approaching the asymptote of the other filter, and so the filters will actually affect each other when you look at the actual real numbers in determining the magnitude of the transfer function, as opposed to the asymptotic approximation. So involving multiple filters, especially the closer the cutoff frequencies are together, the less the design, the actual outcome approaches your design. So this is the approach toward building a bandpass filter with op-amp circuits. The Bode plot will look like this, where you can see here is omega C1, here is omega C2. Two different examples here. This is the gain of 0 dB. This would be a gain of 20 dB, The difference there would be in what you do in the last phase. So in that stage, in that third stage, where you have the inverting amplifier that's setting the gain, basically that stage is used to raise or lower this curve based on what you want and what you want your gain in the passband to be. And now notice that even where we have, in this example, a lower cutoff at 10 and a higher cutoff at 1000, which is 3 orders of magnitude apart, notice that even there, the flat portion of the Bode plot is relatively over a narrow range. So we still have some variation within the passband of what the magnitude function looks like. So this is an example of how you would design a broadband bandpass op-amp filter. Broadband meaning omega C2 is much, much greater than omega C1. So here we find that there's a difference of 100 between the lower and upper cutoff frequencies. So we can say that that approximation will hold and we can proceed with our design. So the way to do this is to design each subcircuit individually. In this example, we want to use 0.2 microfarad capacitors. We want a lower cutoff of 100 and an upper cutoff of 10,000. So remember that the upper cutoff, the 10,000, is actually going to be your low pass circuit. So we design 1 over R low pass C low pass to be 2 pi times 10,000 because these are given in hertz. So you need to convert those to radians per second. So the 2 pi basically takes the frequency in hertz and converts it to radians per second. We've already been told we need to use 0.2 microfarad capacitors. So substituting 0.2 microfarads in and inverting the whole equation, we can find our resistor value for the low pass to be 80 ohms. The high pass would actually be the lower cutoff frequency used in our design. So basically repeat the entire process and you end up with the resistor for the high pass stage to be 7958. Then to build the gain stage, one of the resistors can be selected arbitrarily. So if we select a 1 kilo ohm resistor for the input resistor, okay. So this is not 100% true because obviously you want to design around a resistor value that you can purchase. So yes, it's arbitrary, but if you're actually building this, it needs to be a value that you can actually purchase that's available. So we selected 1 kilo ohm. When we then determined that the feedback resistor should be 2, we have then 2 kilo ohms for our feedback resistor value. So here's what that circuit looks like. Here's the low pass stage, here's the high pass stage, here's the gain stage, and then here's where we would take the output. All right, now if you want a band reject filter, you have to have a slightly different approach. So let me go back a couple of slides to this Bode plot. All right, so here we have cascaded, and here is our cutoff frequency for our high pass filter occurs here, and our cutoff frequency for our low pass filter occurs here, and then here's the pass band. So remember, a band reject has a constant gain, and then it falls off and has an area where we're not passing, and then it comes back up to a constant gain. So the first thought might be that you could just flip the order of these. But the problem is, remember the cascaded op-amp circuit, the transfer functions multiply. So if you put this cutoff frequency over here and this cutoff frequency over here, you're basically going to get zero gain everywhere because these lower gain regions of the filter characteristic mean that basically the low pass filter will always filter out what the high pass filter passes and vice versa. So the approach that is shown in this slide of cascading these together won't work because this one will multiply this one, and this one will be 0 when this one is non-zero, and this one will be 0 when this one is non-zero, so basically you're going to always get 0. So you can't use this kind of an op-amp circuit for that. So instead, what we do to get the band reject filter is we put these in parallel and we put them into a summing amplifier. So instead of taking the product of the low pass filter and the high pass filter, we're taking the sum of those two outputs. So here's our low pass filter and here's our high pass filter, and this is our summing output amplifier. And notice that the two input resistors into the summer are equal, meaning that the RF over RI gain of this last stage is going to be the same for both the low pass and the high pass. And that's important because you want on your band reject filter, you want your low frequency gain and your high frequency gain to be the same. All right, so now let's look at what the Bodie plot would look like for that. So here is the low pass filter, and here is the high pass filter, and then we're going to add these two together and put in the gain. And so what that will look like then is we'll have this region in the center where we reject this range of frequencies. 3 dB down point be about right here, so that will go from about 10 to about 1000. All right, so let's do a design of a band reject filter. So obviously what we're going to do is separately design the low pass and the high pass filters. In this example, we'll go from 100 radians per second to 2000 radians per second, and we would like a gain of 3 in the pass band. So our omega C2 is 20 times our omega C1. So omega C2 being much, much greater than omega C1 is still an approximation that holds, although not as robust as in the previous example. So in this case, the textbook author in this example is using scaling. He's asking you to begin with the prototype low pass filter and use scaling to meet the specifications for cutoff frequency and capacitor value. So once again, the cutoff frequency specification is 100 radians per second. The capacitor value is 0.5 microfarads. So we always calculate our frequency scaling factor first. The prototype filter has a frequency of 1 radian per second. So we want 100 radians per second. So our scaling factor is 100. That then will shift the cutoff frequency. Now the magnitude scaling factor is what we actually use to get the 0.5 microfarad capacitor. So the magnitude scaling factor is determined by what is the capacitor you have compared to what is the capacitor that you want, that you designed around, which was 1 farad. And remember that that relationship encompasses both the frequency scaling factor and the magnitude scaling factor. So to solve for the magnitude scaling factor, we have to use that equation that tells us that the new capacitance is 1 over KFKM times the old capacitance. So to get the new capacitance to be 0.5 microfarads, we find that the magnitude scaling factor is 20,000. That then enables us to determine what our low pass resistor value will be, and it'll end up being 20 kiloohms. So to use a 0.5 microfarad capacitor, we need a 20 kiloohm resistor, and then that should give us a cutoff on the lower end of 100 radians per second. We do the same thing on the high pass end. So the only difference will be our frequency scaling factor is going to be 2000 because of what we want our cutoff to be. That then, using that same design equation for our new capacitor in the high pass part of the filter, we get a magnitude scaling factor of 1000, meaning our resistor value should be 1 kiloohm. So because those cutoff frequencies are fairly widely separated, we can use the ratio of feedback to input resistor in that final stage to get the passband gain of 3. We do that by setting our input resistor to be 1 kiloohm, and we let our feedback resistor be 3 kiloohms, then giving us a gain of 3. Now I do want to point out that the gain is specified in unit list numbers, not in dB. So that's why we're able to do this and calculate this feedback over input resistor value. If you're told you want a gain in dB, so for example, let's say you're told you want a 20 dB gain, you're going to have to convert that to unit list magnitude ratio factors. So you have to figure out 20 times the log of x is equal to 20 dB and solve for x. So now we can just do a final check on what are our actual cutoff frequencies. So if we take 100 and we take 2000 for j omega and we substitute those into the equation, we actually get 2.204 on the lower end, which is a little bit less than the 2.12, which would be our 3 over the square root of 2. So what does this mean? This means that our assumption that these frequencies were very far apart is holding fairly well, but they're close enough together such that the high pass frequencies Bodie plot actually influences the low pass frequency parts Bodie plot and vice versa. So the effect of that is it is moving those cutoff frequencies a little bit because they interfere with one another. They're not completely estimated to be zero. Here's what the final design looks like with the component values entered. And you notice here, you really try whenever possible to keep your capacitor values the same in the low pass and the high pass circuit. And what you're modifying here are your resistor values. And here's the Bodie plot for that circuit. All right, as one final review, we did discuss how it is possible to get a higher order filter by cascading more than one filter together. So this is an example of what happens as you cascade single stage low pass filters together. And here is the Bodie plot showing a first order and then a second order and a third order and a fourth order. And this dashed line illustrates the 3 dB point, 3 dB down point, which would be our defined cutoff. And so you can see illustrated here what we've discussed in class is that this cutoff frequency shifts, the 3 dB point shifts as a function of the order of the filter. The way to determine that shift is to look at the transfer function, which is for an end-stage filter looks like this. We then find the magnitude of that transfer function, force it to be 1 over the square root of 2, and then solve this equation. And when we solve that equation, that's where that little design equation that we've been referring to in class comes from. So the new cutoff frequency for an order of, for a prototype filter where each individual stage would have a cutoff of 1, R is 1 and C is 1, so each one of these is a prototype. We cascade n of these together, the new cutoff frequency will be the nth root of 2 minus 1 all into the square root. So definitely going to lower that cutoff frequency the more of these we put cascaded. So this is very similar to what we did in class, designing a fourth order low pass op-amp filter. We want a cutoff frequency of 500 Hertz and a pass band gain of 10. We want to use 1 microfarad capacitors and we want this to be low pass. So the first thing we do is we solve for omega Cn for a fourth order filter, which we've done previously, and we find out that our correction factor is basically we get down to 0.435 radians per second. Now in the example that I worked out in class, I did 2 different steps. The first thing I did is I took my prototype filter capacitance of 1 farad and I adjusted that based on this 0.435 number. So I took 1 farad and I divided it by 0.435. And then I did frequency scaling factor to get my 500 Hertz. In this example, what the textbook author has done is first he takes 500 Hertz and converts that to radians per second. And then he gets a frequency scaling factor by taking 1 over 0.435 to get the cutoff frequency up to the desired level. And then he also scales simultaneously for the 500 Hertz after it's been converted to radians per second. So in this example, this frequency scaling factor of 7229.22.39 incorporates both the scaling factor due to the fact that you have a fourth order filter, as well as the scaling factor to get you up to this cutoff of 500 Hertz. After that's done and that scaling factor is determined, then based on the size of the 1 microfarad capacitor, the next step is to do a magnitude scaling, is to determine what the magnitude scaling factor is so that you can get the resistor values. So having done that, this is the result. We have resistor values of 138.46. We have capacitor values of 1 microfarad. Then we want to do the final stage. We're told that we want a passband gain of 10. That is not given in dB, that's given in actual gain. So we want an inverting amplifier stage that has a feedback to input resistor ratio of 10. And if we leave the feedback resistor as 138.46, I'm sorry, the input resistor as 138.46, then we can calculate a feedback resistor, which will be 10 times higher than that. And then our transfer function would appear like this. So first, let's look at what that circuit would look like. We have 4 identical low-pass filters cascaded together. And I do want to point out here that there is an error right here. This resistor is off by a factor of 10. So actually that decimal point should be right there. It should be 1384.6 according to what the author actually did. So, so there's your design. And then let's look at the Bode plot. It looks like this. And you can see that we do get 40 dB per decade attenuation in the cutoff region. And we get pretty flat here in the passband up until about 100. Here's our 500 design. Well, actually, this is in hertz. So here's our 500 design value. So just want to remind everyone that when doing actual designs of resistors and capacitors, you must be working in radians per second. The 1 over RC will give you units of radians per second. So even though this plot is done in hertz, the design of your R's and C's has to be done in radians per second. So this frequency would have to be converted. Otherwise, you'll be off by a factor of 2 pi. So that concludes this lecture on review of bandpass, band reject, and higher order cascaded filters.